Imagine you're building a house. You wouldn't just start laying bricks and hoping for the best, would you? You'd start with a blueprint. This blueprint outlines the house's overall structure, the arrangement of rooms, and how everything fits together. This plan is crucial for a successful construction project. In the world of software, we have something similar: software architecture. Just like a building's blueprint, software architecture defines the high-level structure of a software system. It outlines the different components, their interactions, and the principles guiding its design and evolution. A well-defined software architecture is essential for building robust, scalable, and maintainable software systems. It provides a roadmap for developers, ensuring everyone understands the system's big picture and how their work contributes to the whole. This understanding is crucial for effective collaboration, efficient development, and ultimately the success of the software project. Software architecture isn't about the code itself, but rather the decisions made before writing a single line. It's about the system's structure, its elements, and how they interact. It's about making fundamental design choices that impact the system's quality, maintainability, and ability to evolve over time. While code is essential for a functioning software system, it's the architecture that determines its shape and direction. Think of it this way: code is the bricks and mortar, while architecture is the blueprint that guides their placement and ensures the building's stability and functionality. Software architecture is distinct from other design decisions. It's about the big picture, the fundamental structures that shape the system's behavior. It's about making strategic choices that impact the system's non-functional requirements, such as performance, security, and scalability. These decisions have a long-lasting impact on the system's life cycle and are much harder to change later on. To understand software architecture, we need to delve into its core elements, architectural structures. These structures provide different perspectives on the system's organization. There are three main categories: module, component and connector, and allocation structures. Module structures focus on decomposing the system into logically cohesive units called modules. These modules encapsulate related functionalities and data, promoting code organization and maintainability. Think of modules as different departments within a company, each responsible for a specific function. Component and connector structures emphasize the runtime interactions between independent interacting components. Components are the building blocks of the system, while connectors facilitate communication and data flow between them. This structure helps us understand how the system behaves at runtime. Allocation structures address the mapping of software elements to non-software elements, such as hardware, teams, or organizational units. This view helps us understand how the system's architecture aligns with its operational environment and organizational constraints. Let's illustrate these structures with real-world examples. In a web application, a module structure might decompose the system into modules for user management, product catalog, and order processing. Each module encapsulates related functionalities and data, making the codebase organized and easier to maintain. A component and connector view of the same web application might show components like the web server, application server, and database server. Connectors, such as HTTP requests and database connections, would represent the communication channels between these components. An allocation structure for this web application might show which team is responsible for developing and maintaining each component or module. It could also map these software elements to specific servers or cloud infrastructure. These examples highlight how different architectural structures provide complementary perspectives on the system's organization. Understanding these structures is crucial for analyzing, designing, and communicating about software architecture effectively. Section 5. The significance of architectural structures. So what makes a structure architectural? It's not just about dividing a system into smaller parts, it's about making deliberate choices that impact the system's quality attributes such as performance, security, and modifiability. Architectural structures are significant because they provide a high-level understanding of the system's organization and behavior. They help us reason about the system's properties and predict its behavior in different situations. For example, a well-defined module structure can improve code maintainability by reducing dependencies between different parts of the system. A well-designed component and connector structure can enhance scalability by allowing components to be deployed and scaled independently. By understanding architectural structures, we can make informed decisions that positively impact the system's quality and its ability to meet its requirements. Section 6. Architectural patterns, tried and tested solutions. Just like building architects rely on established patterns for designing houses, software architects leverage architectural patterns. These patterns are reusable solutions to common architectural problems, providing proven approaches to structuring software systems. Think of architectural patterns as pre-designed templates that address specific architectural challenges. They capture best practices and experience from numerous software projects, offering a starting point for designing robust and maintainable systems. Examples of architectural patterns include the layered architecture, microservices, and event-driven architecture. Each pattern has its strengths and weaknesses, making it suitable for specific contexts and requirements. By leveraging architectural patterns, software architects can benefit from collective wisdom and avoid reinventing the wheel for common challenges. This allows them to focus on the unique aspects of their system and make informed decisions that align with their specific needs. Section 7. Qualities of good architecture. A balancing act. What constitutes a good architecture? It's not a one-size-fits-all answer, as the ideal architecture depends on the specific context and requirements of the software system. However, some common qualities contribute to a successful architecture functionality. The architecture should enable the system to fulfill its functional requirements, providing the necessary features and capabilities. Reliability. The architecture should ensure the system is robust, stable, and behaves as expected, even under unexpected conditions. Performance. The architecture should facilitate efficient resource utilization, ensuring the system performs well under its anticipated load. Security. The architecture should incorporate security measures to protect sensitive data and prevent unauthorized access. Maintainability. The architecture should make the system easy to understand, modify, and extend over time. Creating a good architecture is about finding the right balance between these qualities. It's about making trade-offs and choosing the best approach based on the system's priorities and constraints. Section 8. The importance of software architecture, building for the future. Software architecture is not just a technical concern, it's a strategic one. A well-defined architecture is crucial for building software systems that are maintainable. Changes can be made efficiently and with minimal impact on other parts of the system. Scalable. The system can handle increased load and accommodate future growth. Reliable. The system is stable, predictable, and less prone to errors. Adaptable. The system can evolve to meet changing business needs and incorporate new technologies. Investing in software architecture is an investment in the long-term success of a software project. It's about creating a solid foundation that supports the system's growth, evolution, and ability to meet future challenges. Section 9. Conclusion: a foundation for success. Software architecture is the blueprint of software development. It's the foundation upon which robust, scalable, and maintainable systems are built. By understanding the principles of software architecture, the different structures, and the qualities of a good design, we can create software that meets its requirements and stands the test of time. As we've explored in this chapter, software architecture is not just about code, but about making strategic decisions that shape the system's structure and behavior. By embracing the principles of good architecture, we can build software that is not only functional, but also adaptable, maintainable, and ready to face the challenges of the ever-evolving technological landscape.